In this animation, we'll try to wrap our heads around a mysterious phenomenon called the Doppler effect. Doctors make use of it to measure blood flow. Police use it to catch our unlawful speeding. And meteorologists use it to track distant galaxies. It's the Doppler effect, an intriguing phenomenon also known as the Doppler shift that was first described in 1842. The Doppler effect is the change in a wave's frequency during relative motion between the wave's source and observer. The easiest way to observe the effect is to consider sound waves. First, a quick refresher on the fundamental properties of sound waves. Sound is a vibration that propagates as an audible longitudinal wave through a medium. Each particle wiggles back and forth, passing its energy onto neighboring particles, and our brains interpret these vibrations as sound. Sounds have two basic properties: volume and pitch. Vibrations with a high amplitude, those that carry more energy, result in louder sounds. Pitch is related to the frequency, which corresponds to the wavelength. The more rapid the vibrations, or in other words, higher the frequency, the higher the pitch. So, those are some of the basics of sound. Now, on to the Doppler effect. A classic example of the Doppler effect in real life is when you are standing by a road and an ambulance zooms past. As the ambulance approaches, it has a high pitch. After it has passed, it has a different, lower pitch. Why does the pitch of the sound or the frequency of the sound wave appear to change as the relative position of you and the ambulance changes? As the wave source, the ambulance, moves towards the observer, you, the center of each newly formed wavefront is slightly closer to you. See how the waves are squished together. The distance between the source and the observer is decreased. Their wavelengths are effectively shortened, so they have a higher frequency, which corresponds to a rise in pitch to the observer. Once the ambulance has passed and is driving away from you, each new wave is formed farther away. The waves are stretched apart, leading to an increase in wavelength. The waves arrive at your ears less frequently. The Doppler effect doesn't just occur in sound waves, but also in light waves, electromagnetic waves, and even water. And it doesn't always have to be the source that moves relative to the observer to cause the Doppler effect. It may be the observer that moves relative to the source. Here is the general formula for pinning down the Doppler effect in numbers. The observed frequency is equal to FO times by the sum of V and VO divided by V minus VS. In this equation, FOBS is the observed frequency, FO is the source frequency, V is the velocity of sound, VO is the velocity of the observer, and VS is the velocity of the source of the sound. Note that all speeds are measured in meters per second, and frequency is measured in hertz. If the source of the sound is moving away from the observer, its velocity value will be positive, and vice versa. Let's try using this equation. Say a car travels at a constant speed of 25 meters per second towards a stationary observer. The car's horn emits a sound wave with a frequency of 500 hertz. If the speed of sound in air is approximately 343 meters per second, calculate the frequency of the sound heard. Let's plug those values into the equation. Since the source is moving toward the observer, the source velocity is positive. The observer is at rest, so they have no velocity. Solving for FOBS, the apparent frequency the observer hears is 539 Hz. That's it for this lesson. Subscribe for more animations like this one, and listen out for the Doppler effect next time you're in a busy street.